Okay, so we can continue on the chapter of the DC glow discharge. So in this chapter, I also got the information, the contents from the Chapman's book. So in this chapter, the Chapman tried to analyze the condition for the stable plasma. So in the last chapter, we have already known the Townsend criterion, the analysis of Townsend, the self-sustaining glow discharge. So in order to keep the discharge as a stable condition, one need to apply a DC bias voltage between cathode and anode, and also adjust the pressure in the system to a certain range, so that the plasma can be initiated and can sustain for a long time. But for those kind of plasmas, the current density flowing through the cathode surface and collected by the anode surface, the current density must be high enough. So that's from the previous chapter. And in this chapter, the Chapman analyzed the discharge in more detail and try to find out in the actual system what is the most important factors, for stable DC glow discharge. Okay, so in the first part, we have to consider the loss of charges. So in previous chapter, we just know about how can we supply the charges, right, including electrons and cations, right? So if we keep the current density to a certain larger than a certain value, we can generate the plasma. So if one electrons are coming out from cathode surface, when the electron travel all the way to the surface of anode, during the path from cathode to the anode, the gas inside the system can be ionized. And also when cations bombard the cathode surface, the cathode surface can also emit electrons. So we know there are at least two sources for the charges. One is inside the gas, caused by electron impact ionization, and the other one is from surface of cathode. And in this chapter, we will also consider the surface of chamber wall and surface of anode. So from these surfaces, electrons can be emitted out by bombardment, by ion bombardment, or by electron bombardment. Okay, and so in the next few slides, Chapman give an example with selected a value of the ion density and the current density flowing through the cathode and anode, and consider some of the charges will lost to chamber wall, will lost by recombination, and the energy will be lost, right, by heat transfer and by light emission. So in order to keep the plasma as a stable condition, one need to supply energies supply energy and also need to supply the electrical current. Okay, so one needs to balance the energy and balance the loss of charges. So in the next few slides, we'll see the way to compensate the loss of the electrons by secondary emission from the surface, from cathode, anode, and the chamber wall. And Chapman give the examples with selected values to let us know whether these processes are enough for keeping a stable discharge. Okay. So first we are focused on the secondary electron emission from these surfaces. So the secondary electrons were emitted from a solid surface after the bombardment by electrons, ions, neutral particles, and photons. Okay. And this one is the secondary electron emission by electron bombardment. Okay. So as we have already known, inside the plasma, the electrons possess high velocity or high energy. Okay. So these electrons can reach the surface of chamber wall, the surface of anode, and some of the electrons can reach the surface of cathode. Okay, surface of cathode. So if these electrons collide with the surface of the material surface will emit electron, and this is the first type of the secondary electron emission. Okay, and left figures shows the relative secondary electron emission yield. Relative, and the horizontal axis is the energy of electron. So in this case, if you use an electron beam with the average energy of electrons a little bit higher than 150 volts. So for example, if you use an electron beam with 160 volt accelerating voltage, okay, you can run this kind of experiment in a scanning electron microscope. Scanning electron microscope. So first you need an electron source. So there are different types of electron source, and you can call this as the electron gun. Okay, so you can use the high electrical field to extract electrons from a solid material, or you can use the hot tungsten filament to extract, to let the electrons coming out. So between these five, the electron gun and also bias is the cathode. Okay. So between the tip and the opening ring of the anode, there is a very strong electrical field. Okay. So you can use this setup to pull out electrons from tungsten, hot tungsten surface. Or maybe you can use zirconium oxide. That's for another type field emission. Okay, so once the electrons are pulled out, you can use another electrode for the acceleration. Okay, so that the electron beam can come all the way to a piece of the specimen or a piece of anode. Okay, so this is the electron beam. So under scanning electron microscope, there are different lenses, the electrical magnetic lenses, so which can change the size of the beam, and then let the electron beam focus to the surface of the specimen. Okay, and there is another there are another X and Y scanning circuit, so that the beam can scan to different locations. Okay, this is by XY scan circuit. So this is the fundamental hardware of scanning electron microscope. Okay, so inside the SEM, there is an electron beam, E-beam generated by this kind of setup. Okay. Okay. So let's take out the XY scan. So if you just let the electron beam strike at the center of the specimen, you can place different detectors nearby. Different detectors. To collect secondary electron. Okay, so the secondary electron will come out. Also, the backscattering electron. So the surface of the specimen will emit electrons. So here are two types of the electrons emitting out from the surface of this species surface. Okay. So on the right side, we can find out these electrons emitting out, or actually they are reflect back from surface of the specimen. It's named backscattering electron. And this part is from secondary electron. So the energy of secondary electron is very small. And the energy of backscattering electron is equal to the energy of the incident electron beam. Incident electron beam. So if you use 160 volt of E-beam to strike the surface, the backscattering electron also have an energy of 160 volt. Right. So if you use higher accelerating voltage for your E-beam, for example, if you use the 10,000 volt of the accelerating voltage, you got a E-beam with the energy of 10 kV. The backscattering electron will also have the energy of 10 kV, backscattering electron. Okay, so the backscattering electron is caused by the reflection of electron beam. And secondary electron emission is different from backscattering electron. The secondary electron emission is caused by some inelastic collisions between the incident electron beam and the atoms on near the surface of your specimen. So after multiple collisional process inside your anode material, the atoms near the surface of your specimen will emit electrons out, and this part is called secondary electron. Secondary electron, okay. So people use the backscattering electron and secondary electron to run the use the XY scan to get the mapping information and get images, right? For the secondary electron beam, secondary electrons, you can form SEI image, secondary electron image, and from the backscattering electron, you can get a BEI image. So these two are the basic image from the scanning electron microscope. Okay, and in our class, in this slide, we are just like to know how much the ratio of the secondary electron emission by electron bombardment. Okay, so for example, this is the secondary electron emitted from silver, and the right figures shows the secondary electron emission from different metal surface. So if we look at these few curves, silver, tungsten, copper, and moly is pure metallic materials. If the incident electron beam has an energy about a few hundred electron volt, for example, 250 electron volt, right? The secondary electron emission yield is about 1 for these metals. Secondary electron emission. Okay. And for beryllium, the secondary electron emission is less, the yield. And you can use the simple delta for the secondary electron emission by electron bombardment. So the delta equals to the number of the electrons emitted from surface of the material per electron bombardment. So this part is the number of incident electron. This part is the number of emitted electron. The ratio is secondary electron emission yield, or secondary emission ratio, delta. Okay. And the here is another source for the electron emission, and it is from the ion bombardment. So in the plasma, in plasma, there are different species, and the most important species are the species are electrons, cations, and metastable or radicals, metastable species. Okay. So if you generate a plasma, and then you can find out the cathode will be bombarded by ion. And the energy of ions depends on the cathode force, or depends on the applied voltage. So in a normal or in a regular DC discharge system, you can apply a voltage of few hundred volts, right, to generate plasma. And the potential, right, the voltage difference will be limited to a space near cathode. So in a specific name, the layer is named cathode layer, right? Cathode layer. So all the potential drop will be located in the cathode region. And the ions, when ions travel through the cathode layer, they can gain energy by the potential drop. So you can make the ion bombardment with the ion energies of few hundred electron volt easily, okay. But in these two pictures, we can see the horizontal axis, right? The horizontal axis are the ion energy, ion kinetic energy. So in the left figure, the ion energy can be a few hundred electron volt to 1,000 electron volts. In the right figure, the ion energies can be 10 to 4 or 10 to 5 electron volts. Okay, so if you want to generate an ion beam with such high energy, you need an ion beam source. So this experiment was conducted in the ion beam system, not in a plasma system, in ion beam system. Okay, so in the ion beam system, you can actually control the ion energy, the incident ion beam. Okay. So from this figure, we can see the secondary electron emission. Secondary emission for ion bombardment, the gamma sub I, is related to the ion energy, instant ion energy. So if you increase the ion energy from 100 volt to 1,000 volt, 1,000 volt, right? You can see the secondary emission for the ion bombardment will also increase, or even when you increase the energy of ion beam to 10,000 electron volt, the secondary emission will also increase, right, up to a few digitals, okay. But in our plasma, DC plasma system, usually the cathode force is smaller than 1,000 volt, So if you are making a system, generating a plasma system with a bias voltage less than 1,000 volt, we can just focus on this figure. Right. So in this figure, the solid line is bombardment of the tungsten. So you can use different ions to bombard tungsten, and the dashed line is the bombarding the molybdenum target. So the secondary emission for the ion bombardment is smaller than 1. Usually it is smaller than 1. So per ion bombardment, only 0.24, 0.25 of electrons will emit out by the ion bombardment. So you can get an idea how many electrons can be knocked out by ion bombardment. And in the last slide, the secondary electron emission by electron bombardment is close to 1. Close to 1. But the secondary electron emission by ion bombardment, are always smaller than 1 in a plasma, DC plasma system. But if you can generate electron beam with such high energy, the secondary electron emission by the bombardment of these high energy ions can be higher than 1 or than 3. Okay. And the secondary electron emission by ion bombardment also depends on the surface structure of the material. Surface structure of material. So in this slide, here are 4 figures. So if you use argon ion to bombard the surface of nickel, single crystal, right? So if you bombard the nickel surface by high energy argon ions, you can use a detector to collect secondary electrons or collect the electron emitted out from the surface and get the secondary electron emission yield. And from this figure, you can see for the single crystal nickel, the 111 surface can emit secondary electron easily, right, compared to the 100 surface and 110 surface. So, and here is the argon ion bombarding the aluminum surface. Also, 111 surface can emit electrons easily, and 110 is the capability of electron emission is less than the 111 surface. So all this, and also silver, because nickel, aluminum, and silver have a FCC structure. And for the FCC structure, 111 surface has the highest packing density of atoms. And if you use molybdenum single crystal and use argon ion beam to bombard the molybdenum surface, you will find out the 110 surface has highest secondary electron emission, because molybdenum is BCC crystal, body center cubic crystal. So for the body center cubic crystal, the 110 surface has the highest atomic packing density. Okay? So if you can conduct this kind of experiment, you can find out the different secondary electron emissions from different crystal planes. Okay, but usually if you use these metals as the cathode or anode material, you will always use the polycrystalline cathode and anode. It's difficult to make a large size of metal single crystal. But if you run the experiment by using a single crystals with different plane surface, you can find out the differences. Okay. Okay, so last slide let us know that the secondary electron emission depends on the crystallographic plane, depends on the 111 plane, 110, or 100 plane. Depends on the plane, crystallography plane. And in this slide, these three figures tells us the secondary electron emission also depends on the surface condition of the material. Okay, so usually when we run this kind of experiment, we need a vacuum system. But in a vacuum system, if you use pumps to pump out the air, okay, and usually you cannot remove all the gas molecules. There will be a small amount of the gas molecules remain inside the system. Okay, so if you place a piece of metal, for example, tungsten, inside the vacuum system, and depends on the pressure of your vacuum system, you will find out the surface of tungsten. At the beginning, it might be very clean, but later on, the residual gas will adsorb on surface of tungsten. So at the beginning, you might have a piece of tungsten with clean surface. But later on, after a few minutes, the surface of the tungsten might absorb nitrogen, a thin layer of nitrogen. So if you run the experiment to measure the secondary electron yield from tungsten surface, okay, you can find out the differences. So in the upper curve, you can use helium ion beam to bombard the tungsten surface and get the secondary electrons, and then calculate the secondary electron yield. So for the clean tungsten surface, the secondary electron yield might be about 0.30. And later on, when a monolayer of nitrogen adsorbs on surface of tungsten, the secondary electron yield will drop. Okay, so the secondary electron emission also depends on the cleanness of the metal surface. If there are some molecules adsorbed on the surface, the secondary electron yield will also change. Okay, Okay, and in the right figure, at the beginning you have a piece of tantalum, and then you can place tantalum inside the oxygen, nitrogen, or hydrogen gas, and let it stay for a while, so that the surface So at the beginning, the surface of tantalum, for example, right, is absorbed by oxygen. Oxygen. This is at the beginning. And later on, after you run the argon ion bombardment and majorly secondary electron yield for a while, okay. Some oxygen, adsorbed oxygen molecules will escape away after the ion bombardment. And then eventually the tantalum surface will become a clean surface. Okay, so from this experiment you can find out they are after the bombardment and then the secondary electron yield increase from this figure. So this part, these three curves are the surface, the tantalum surface adsorbed with oxygen, nitrogen, or hydrogen. Right. And the upper curve is the tantalum surface, right? Clean tantalum surface. Clean tantalum surface. Okay. So all these three figures tells us that the gamma I secondary electron emission by ion bombardment also depends on the conditions of the metal surface. Condition. And previous slide showed us the secondary electron emission yield depends on the crystallographic plane. Crystallographic plane. Okay. And okay. And in this slide, the energy of the secondary electron is quite small compared to the back reflected or back scattered electron. And this slide shows the energy distribution of the secondary electron by helium ion bombardment, right? So you can use helium ion to bombard molybdenum surface and collect the secondary electron by a detector. Just like the detector placed inside the SEM, okay? And then measure the energy of the secondary electron. So you can find out these secondary electrons has the energy, right, in the range here from around 5 to 10 electron volts. 5 to 10 electron volts, okay? And this is a typical energy distribution of a secondary electron. Okay, and this slide shows the secondary electron emission by neutral particle bombardment. So there are electrons, ions, and the neutral particles inside the plasma. So when the neutral particles or neutral species collide with the solid surface, they might also cause the electron emission. Okay. So the ordinate is the electron emission yield, secondary electron emission by the metastable bombardment. Okay. Here, this curve by energetic radicals, energetic neutrals. Okay. So compare to the secondary electron emission by ion bombardment, the secondary electron emission secondary electron yield by neutral bombardment is much less. Much less. Okay. So for example, if you have neutral particles with energy of 1,500 volts, the electron yield, secondary electron emission yield, is about only 0.03. 0.03. But if you use high energy ion, like 1,500 volts of the ion beam to bombard the surface of metal, the emission, secondary electron emission yield might be higher than 0.1. Higher than 0.1. Okay. So there are different species in plasma, so that we can find out the electron emission yield is highest in electron bombardment, and then ion bombardment, and the neutral bombardment. Neutral bombardment has a secondary electron emission yield much less than the previous two. So the neutral bombardment is irrelevant to plasma or to the maintaining of the discharge. Okay. Okay. And the last one is secondary electron emission by photon bombardment or by photo irradiation. And this kind of the electron emission has a name, is named the photon emission. When you irradiate a piece of material by photons, the surface of the material can emit electron out. And this kind of the process has a name, photon emission. Photon emission, okay. So the photon emission yield depends on the energy of photon. And inverse of the energy of photon is wavelength. So in this figure, the horizontal axis shows the wavelength of photon. Okay. So from 400 angstrom to 4,000 angstrom to 7,000 angstrom, right? This part of photon belongs to visible light. Okay, and for the wavelengths smaller than 4,000 volts, fall into the region of UV light, okay. And we have already known in a plasma, inside the plasma, there are different kinds of collisional process. So for the recombination process, when electrons meet a cation, they recombine together and lost the negative and positive charge. But in the meantime, this process will give out light, and usually the light belongs to the UV for the recombination process. And for the neutral particles, when they relax from radical state or high energy metastable state to ground state, they will also emit light. And this part of light belongs to a visible light. Okay. So you can convert the wavelength of light to energy of photon. Energy of photon. So if the energy of photon is higher than the ionization energy of gas species, right? These photons can ionize the gas. And if the energy of photons is higher than work function of a solid material, you can also get electrons coming out from the solid surface. Okay, work function here. Okay, let's take a 10 minutes break.